Welcome back. My name is Aaron Dolan. This is the third lecture in a series on electrical engineering principles. We're going to talk about series and parallel circuits. As a starting point, I thought it might be interesting to take a look at the propulsion of this World War II submarine. This particular vessel is moored in Pearl Harbor, and it is a museum ship that you can visit. I've been there. It's actually an interesting visit, amongst the other things that you can see while you're in Pearl Harbor. On this page, which is maintained by maritime.org, we can see how these submarines were constructed. We have the fore battery and the aft battery. Each battery has 126 cells. Each cell is about 2 volts nominal. That gives you a 250 volt battery bus, again in your fore and aft groups. Each battery is huge. It weighs 1,650 pounds, which gives you about 210 ton of battery on this vessel. I'd like to draw your attention to the motors. Here we have 2 motors side by side that are joined through a reduction gear going to the shaft. Here's another 2 side by side, reduction gear going to the shaft. Now that's one way to design the vessel. Another way is to have 2 slow speed motors that are mounted front to back, like so. Either way, there are 4 motors, so remember that. On each submarine, there is a control console that allows the operator to control the speed of the motors and direction as well. So you have these large levers that you would pull to engage the various motors. If you're curious, there's a wire diagram here. What I wanted to show you, though, is how these motors can be connected up to the bus in series or in parallel. Let's go ahead and sketch that out. This is our symbol for a battery, with the larger bar being the positive. Sometimes you'll see the polarity indicator there as a plus. This is the symbol for a motor, where these represent the brushes of that motor. Now, if you wanted the submarine to go fast, here is how you would configure the batteries. You would take the fore battery, and you would take the aft battery, and you would connect them in parallel. You can see the batteries are like so. You have positive to positive and negative to negative. Then you would take each of the 4 motors and route those in parallel as well. With this configuration, each of these motors would have 250 volts applied across its terminals. And we would call this a parallel arrangement. If you didn't need the speed, you could use a series connection instead. That looks something like this. In this configuration, the motors are in series, one after the other. You now have 125 volts DC on each motor. Again, the batteries are connected in parallel to give us a battery bus of 250 volts, but each motor receives half of the voltage because the motors, again, are in series. Whereas before, in parallel, each motor received 250 volts. There was another configuration called slow, and I'll show you what that looks like. In this configuration, known as the slow configuration, we see that all 4 motors are connected in series, which means each motor will receive about 62.5 volts DC. Again, that would be measured via voltmeter as attached there. Right? If you measured that, that's what you'd see. You'd see 62.5 volts. Here, if you used a voltmeter, for example, across that motor, this is the series configuration, you would see 125 volts. And here, if you installed a voltmeter across the motor, you would see 250 volts. That gives you a little idea what these controls are for. They allow you to configure the motors between slow, series, and parallel. While we're here talking about motors, let's look at a resistor circuit that you might find on that submarine. This is one of the batteries. We'll add a switch, a large resistor, and then the motor. If we were to turn this system on, or if we were to look at it as a function of time, okay, so we're going to graph the performance of the motor, we would find that the speed of the motor does something like this. So this is the motor speed. That kind of makes sense, right? If you're looking at the output of the motor, as soon as you applied power, right, as soon as you closed this switch, it would take a certain amount of time for that motor to come up to speed. In the meantime, the current, because it's going through this resistor, there's a limit to how high that current can be. The current would do something like this, and it would settle out to a certain current. Again, we could continue on there, and you would see we'd reach steady state. But remember, we don't want to stay there for too long because this resistor is giving off a lot of heat. So what we can do is we can put another switch in here, and this time, after the motor has started and gotten up a little bit of speed, we can close that second switch. What will happen is the motor will once again come up to a higher speed, but the current will do this. Again, the current will jump up again, and then it will settle down to a new steady state value. Again, this is current for the motor, I motor, and this is the rotational velocity of the motor itself. That two-step process you see here, where you start with resistance and then you cut the resistance out, is important because without it, you would have started with a very high current, which would have taken time to dissipate. And this is not a good place to be. That high current can damage the equipment. It can also damage contacts. So to avoid that, again, two-step process. Step one, you start with resistance, and then step two, you take the resistance out and you have full power to the motor. Well, that was a good place to start. Let's get down to business. We start with a quick review. You'll recognize this as Ohm's law. And you'll recognize this as the power law. And using the cover-up method, you could determine any of the values. For example, voltage is a current times a resistance, and a power is a current times a voltage. We mentioned that there were a few more if you did the algebraic manipulation between these two, where we said power is also equal to current squared by resistance is equal to voltage squared divided by resistance. And these two can help you out because they make the problems a little bit simpler. They take a two-step process and make it a one-step process. From the lab, you remember the purpose of resistors. So you had a circuit that was very simple like that, and you determined that the resistor converts electrical energy into heat, and in the lab you verified that this property was true. There was a linear relationship where you plotted the voltage and the current, and you saw a linear relationship between those defined by the resistor that you had installed in the circuit. I believe we talked about this. If you have a vertical line, that's a short circuit. And if you have a horizontal line, that would be an open circuit. KVL was another thing we explored. And we said that the summation of the voltages in a closed loop was equal to 0. As an example, take a look at this circuit. We'll let this be 5 volts. We'll let this be 10 volts. We established some rules in the class where we said we are going to take a journey. We're going to start in the lower left-hand side of the circuit and go around the loop. If we enter a power supply from the negative terminal, we would call that negative 5. Here again, we do the same. So this is minus 10 plus voltage on the resistor is equal to 0. Therefore, the voltage on the resistor is 15 volts. This circuit can be more complicated. Let's try this one. So here we have 2 resistors and 3 power supplies. We'll let this be 2 volts. We'll call this R1. We'll call this R2. 5 volts and 10 volts. In this circuit, there are 2 loops. We'll call that loop 1. We'll call that loop 2. It's actually a 3rd loop as well that goes around the outside. Let's go ahead and solve for those loops. Again, we start in this corner. We're going to make a journey in that direction. So we call this negative 2 plus VR1 plus 5 is equal to 0, which means that voltage on R1 is equal to negative 3 volts. So if you were to look at this, that's negative 3 volts. Solving for the second loop, we would start our journey here and go in that direction. We would say negative 5 plus VR2 minus 10 is equal to 0. So the voltage on R2 is equal to plus 15 volts. So we can write a 15 here. And now we can take a journey for the outer loop. And that works out as negative 2 minus 3, which we recorded here as minus 3, plus 15 minus 10 is equal to 0. And yes, that is a true statement. Therefore, we see that all 3 loops are consistent. Kirchhoff's current law was another property we explored. We talked about nodes. For example, if you had 10 amps going in and 5 amps going out, how many amps would you have leaving? Well, you would say the goes intos equals the goes outas. In this case, you have 10 in, and you have 5 plus x leaving. Therefore, x is equal to 5. We played with some more complicated examples. Maybe you have a current source up here, and we'll put a resistor there. We'll put a better resistor here. If there are 7 amps of current flowing here, you would explore this node. So notice the current source, which I should make a little more clear, has a current flowing in that direction. So we have 7 amps and 2 amps flowing in, which means we have 9 amps flowing this way. That brings us to this node where we have 9 amps in, 2 amps leaving, which means we have 7 amps going in this direction. And that's kind of an interesting property because that means that if you have a node that's floating all by itself out here, and you have a wire in and a wire out, we don't really care necessarily what's happening inside the node. We can just make the assumption that if 7 amp flows into that, there must be 7 amps leaving it as well. Now we can move on to talking about resistors in series and in parallel. So let's start out with this circuit. We have 3 resistors. We'll let R1 be 2 ohms. We'll let R2 be 3 ohms, and R3, we'll let that be 5 ohms. And what we're going to do is we're going to sit here, and we're going to look into the circuit. And when we say look into the circuit, that basically means is we have our multimeter, and we are going to use the 2 probes to look into the circuit to see what the actual value of the resistance is. If you have resistors in series, the formula is very simple. You'll want to put this one on your note card. The total resistance is equal to the sum of the resistances. And that holds for any number of resistors that you might have. So again, this is a series circuit. So when you have resistors in series, this is the formula. For our example, we would say our total is equal to 2 plus 3 plus 5, which gives us a total of 10 ohms. Another way of saying that is the equivalent circuit looks like that. So from our observer's perspective, you can't tell the difference between the first circuit, the top circuit here, and this circuit. They are identical. Again, if you were to put the circuits into a box and I asked you which one was which and all you had were the probes, you wouldn't be able to tell the difference because they are identical. So that was series resistors. Now we're going to explore parallel resistors. Put a string of parallel resistors. We'll let R1 be 20 ohms. The R2, let that be 10. And in R3, we'll let that be 30. Once again, from the observer looking into the circuit with a multimeter, this is what you would receive. You would see that the total resistance is equal to 1 over R1 plus 1 over R2, and in general, to 1 over R to the n. Okay, so it's the sum of the reciprocals. That's one way you could write it. You could also write it this way, where you said 1 over RT, that's R total, is equal to 1 over R1 plus 1 over R2 plus, and going on to R. Let's see how this works on a calculator. So you take the first value and you invert it, add it to the inverse of the second value, and add it to the inverse of the third value. There's an intermediate answer, and then we take the inverse of that answer. And that is the equivalent resistance. So from our outside observer's perspective, this circuit, again, that parallel circuit with the 3 resistors above, has a value of approximately 5.45 ohms. Something to notice here. This value will always be lower than the lowest resistor in your parallel circuit. In the series circuit, this value of the equivalent circuit, that is, will always be higher than the highest resistor in the circuit. So keep that in mind. That's kind of a sanity check. As a side note, let's go back to this parallel resistor form. If you only have 2 resistors, that's what it looks like, right? And I'll let you guys do the math, but what you'll find out is that R total is equal to R1, R2, right? So the product over the sum of the resistances on the bottom. This is the only time you're ever going to hear me talk about that, because in my opinion, this is more bother than it's worth when you start out. Because remember, it only holds true for 2 resistors, and people will try to force it and do 3 resistors or make other mistakes with it. So personally, I would use this form here. I suppose if we were doing hand calculations, this trick where you do the product of the resistors over the sum of the resistors would make sense. But for our purposes, a calculator will always be within reach. We talked about resistors in series. We talked about resistors in parallel. Now we're going to talk about series parallel circuits. Here is an example. Let this be R1 with 5 ohms, R2 with 10 ohms, R3, 5 ohms, and R4 with 5 ohms as well. Your observer is here looking into the circuit. These particular problems are like a puzzle. It's very useful to do only one piece at a time. For example, you'll notice that those two together are in series. We could replace those two 5 ohm resistors that are in series with a single resistor and then redraw the circuit. R1 remains unchanged at 5 ohms. R2 remains unchanged at 10 ohms. Our observer is still out here looking into the circuit, but now this resistor on the end has been changed to 10 ohms. So our circuit is a little simpler now. We've moved one step closer to solving what the equivalent circuit is. Let's get a different color here. You'll notice that these two are in parallel. And we know how to solve for that. Our observer is still out here looking in. The 1 ohm, R1 remains unchanged at 5 ohms. However, this has now been simplified to 10 in parallel with 10. So 10 inverse plus 10 inverse equals inverse equals. And what I just did there was I said 1 over RT is equal to 1 over 10 plus 1 over 10. And solving for that, our total, which is now this piece in green, right? That is 5 ohms. One more step and we are done. We recognize that this piece is in series. Oh, we didn't put that in there, did we? This is 5 ohms right here. Sorry about that. Our observer is still out there. And now the entire circuit has simplified into this. It's just those two in series, so 5 plus 5. That's 10 ohms. And done. This circuit, our original circuit, is indistinguishable from this circuit. Again, that assumes that you are looking into the circuit with your multimeter. Right? You're looking into the circuit. And what do you see? You see 10 ohms. All right, nobody wants to do this. I get it. It's a lot of steps. It's a lot of writing. But I would encourage you, especially when we start out, be very methodical and do each step. Redraw the circuit so you can keep track of where you are. Later on, when you're more experienced, this will be a piece of cake and you'll just write the numbers very quickly. But for now, again, step by step by step. We'll spend the rest of our time working through a few examples so you can get a feel for how these problems are laid out. Let's take this problem where the observer has looked into the circuit and declared that the total resistance is equal to 6.6 ohms. Okay, so this is different. This is different than before because here we already know what the value is when we look into the circuit. We also know that the circuit has a 20 ohm resistor, it has a 30 ohm resistor, and it has one more resistor, but this resistance is unknown. And your job is to find out what is the value of that R3, because we don't know. We go back to our resistor formula for parallel resistance, and we say 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And now we substitute the values in. So we said the total resistance is 1 over 6.6 is equal to 1 over 20. That's plus 1 over 30 plus 1 over X. And if you were to solve that, you would find out that X is equal to 15. Let's do that in the calculator. So you take 6.6 invert minus 20 invert minus 30 invert equals, and then you invert that, and there's the answer. X is equal to 15 ohms. Here's another problem. We want to find the power in the source given this circuit. All right, so this one, what we want is we want to know the power. How much power is that source supplying to the resistors? This is a multi-step process. So here we go. Let's give it a try. The first step is to calculate the total resistance. So R total is equal to 2 plus 5 in parallel with 7. That's a shortcut there. We use the parallel bars because you recognize that there are two pieces here. We have this box, right? We have the box containing the 5 ohm and the 7 ohm, and those resistors are definitely in parallel. And then we have that resistance in series with the 2 ohms. So that gives us this equation. We can solve that in the calculator as 5 inverse plus 7 inverse equals inverse equals. So the box, right, this box right here has a resistance of 2.9 ohms. Right, so this is equal to 2 plus 2.92 ohms. And then we add 2 to that. Plus 2 equals. There we go. So the resistance of R1, R2, and R3, when you look in with the meter, would give you 4.92 ohms. You remember what the problem asked for, though. We wanted to know what is the power given off by that source. There's two ways you could do this problem from here. You could say the current on the source is the voltage divided by the resistance total, which is 18.5 over 4.92, which gives you 3.76 amperes. From there, you could say power is equal to a current times a voltage, which gives you 3.76 times the voltage. There it is, at 18.5. So the power is approximately 70 watts. But be careful, that's not quite true. Because this particular power supply is supplying, which means the power, if you wanted to think about it, is 70, but it's supplying. Or you might even see it referred to as power is equal to negative 70 watts. Again, because that power is coming out of the supply. So I said there's two ways you could solve this. The other way you could have solved this problem, method 2 if you prefer, would be to say that power is equal to voltage squared divided by resistance. So power is equal to 18.5 volts squared. Again, that was the source voltage right there. And that is divided by the total resistance, which we declared to be 4.92. So let's see if that works out. So 18.5 squared divided by 4.92, and that is equal to, 70 watts. Again, you have to be careful and specify that that's being supplied. Let's take another look at this problem. So we had 18.5 volts. We had an R1. We said that was 2 ohms. We had 2 resistors. We had an R2 that was 5 ohms. We had an R3 which was 7 ohms. We did some calculations and we determined that the current here was 3.76 amps. With that information, we will be able to figure out the current for either of these resistors. For example, we'll pick on the current for R2. Know that R2 and R3 are on the same node, and things that are parallel have the same voltages across them. So keep that in mind as we continue on here. Well, if in doubt, take a walk and see what you can come up with. So if we walk here, we see negative 18.5 plus VR1 plus VRX. Can I do that? Can I say that this right here is the voltage on resistor X? Right? So we'll say that, and that is equal to 0. Now we know something about the voltage here. We know that the voltage there is actually 2 times 3.76 amps. Why do we know that? Why do we know that? Let's see. Ohm's law. So a voltage is a current times a resistance. So what we're doing is we're substituting in this resistance and this current to give VR1. So we can rewrite this as negative 18.5 plus 2 times 3.76. So that's plus 7.52 plus VRX is equal to 0. So VRX is equal to 11 volts, which means there's 11 volts across this node right here. So if you were to put a voltmeter there, it would read 11 volts. And that's enough. With that information, we can calculate the current on this resistor. So we wanted R2. Using Ohm's law again, we would say the current on R2 is 11, again that's this voltage here, divided by the resistor, which is 5. So the current on R2 is equal to 2.2 amps. So 11 divided by 5. 2.2 amps. I'll tell you right now, that was the hard way to do this particular problem. In the next class, we'll explore something called a current divider and a voltage divider, which will make this task much easier. Not so many steps, much faster. Let's continue on with our examples. Suppose I gave you a bag of 5 ohm resistors and asked you how many different combinations you could make. Let's find out. You could say, fine, here's one resistor, 5 ohms. That's a good answer. That's one combination. You could put the resistors in series, and you could say, I have 5 ohms and 5 ohms. The result is 10 ohms. And you could carry that on indefinitely. So maybe you put 3 resistors together, and you say 5 ohms plus 5 ohms plus 5 ohms is now 15. So there's an infinite number of resistors you could go in that direction. So it'd be 5, 10, 15, 20, 25, and so on to infinity, or until you ran out of resistors. You could go the other way. You could say, well, we will put 2 resistors in parallel. So 1 over RT is equal to 1 over 5 plus 1 over 5, because those are the parts I gave you, right? A large bag of 5 ohm resistors. So we come here, so 5 inverse plus 5 inverse equals inverse equals. So we would say that's 2.5 ohms. And maybe 2 wasn't enough, so now you do 3. And what do you get there? So 5 inverse times 3 equals inverse equals. So now we're down to 1.6 ohms. Again, you could do that infinitely number. You could do that infinitely number of times and arrive with a smaller resistance every time you do it. So those are the simple ones. You could do series circuits. You could do parallel circuits. You could also do series parallel circuits. So try that one out. Again, all of these resistors are 5 ohms because that's what I gave you in the bag. So what is the resistance here? One way to solve that is to put a box around this piece and say 3 resistors in parallel is about 1.6 ohms. Put a box around these and you would say 2 5-ohm resistors in series is 10 ohms. So the total resistance for this one is about 11.6 ohms. Again, there's so many different variations you could play with on that. Let's try a car example. Let's say you have a 12-volt DC system, and I gave you a 20-ohm resistor and a 40-ohm resistor. How many different ways could you put those two together and tell me which power you would get out of each configuration? Here's one. You could take those 2 resistors and put them in series. So 12 volts, 20 ohms, 60, nope, correction, that was 40 ohms, wasn't it? 40 ohms, right, 20 and 40. So we would say the power in this circuit is the voltage squared, so 12 squared over the resistance. Because they're in series, you would just add them up. So in this case, the power is 2.4 watts. So again, with a 12-volt supply, a 20-ohm resistor and a 40-ohm resistor, one way to connect them is to get 2.4 watts. You could say one way to connect the circuit is not to use the 20-ohm resistor. Didn't say you had to use them. So there's 40. So the power in this case is voltage squared divided by resistance is 12 squared over 40. So the power is now 3.6 watts. So there's 2 ways that you could build that circuit. Next, you could choose to use only the 20 ohm resistor. So 12 volts, 20 ohms. This is starting to get repetitious, isn't it? Voltage squared over resistance, 12 squared over 20. So the power is equal to 7.2 watts. So there's 3 ways. And the last way you could set up these particular resistors with the 12-volt power supply is to say there's a 20, here is a 40. There's a 40, again 12 volts. 1 over R total is equal to 1 over 20 plus 1 over 40. Solving for R total, we get 20 inverse plus 40 inverse equals inverse equals. So that's 13.3 ohms. Power is equal to voltage squared divided by resistance. 12 squared over 13.3. The power is therefore about 10.8 watts. So given a power supply of 12 volts, a 20 ohm resistor, and a 40 ohm resistor, these are 4 different ways you could configure them. You could configure to deliver 2.4 watts, 3.6 watts, 7.2 watts, or 10.8 watts. One more problem and then we'll call it a day. Let's take this one. For this problem, you're asked to solve the current for R2. So we have an R1 over there, an R2 over there, and an R3, like so. Your opening move is to establish that box around these parts and calculate the total resistance. So 4 inverse plus 6 inverse equals inverse equals. So our total for that particular box is 2.4 ohms. I'm going to do a little trick to make this problem simpler. I'm going to swap these two parts. In a series circuit, because the current is the same everywhere, it will not affect the circuit performance or operation if you do that. Let's move the power supply over to the left side. That way we have a left to right flow in our circuit. We'll move the resistor here. Again, we can do that because it's a series circuit. 2 ohms, 10 volts, so 2.4 ohms. Our total is equal to 2 plus 2.4 is equal to 4.4. As a shortcut, you could have said that our total is equal to 2 plus 4 in parallel with 6. As we go along, you'll be able to put that in your calculator very quickly. So 4 inverse plus 6 inverse equals, and then 2 plus answer equals. There we are, same answer, 4.4 ohms. From there, you can calculate the current. So the current on the supply is the voltage divided by a resistance. It's equal to 2 over 4.4. So that gives us 2.27 amperes. And now we can do the loop to calculate this particular voltage drops. So we said this current was 2.27 amps. If we walk the loop, and this is the same problem we did before, I'm just showing you it again, we would say negative 10 plus 2 ohms by 2.27 plus the voltage on the box is equal to, so we ran out of room here, we'll erase that, is equal to 0. So the voltage on the box, again that's this box here, the voltage on that box is equal to 5.46 volts, which means the voltage here, right, that's that voltage, is 5.46 volts. And if you knew that, you could calculate the current. You could say that current is 5.46 divided by 4. You're like, well, where'd that 4 ohms come from? That's this guy right here, right? Because we know the voltage across the resistor, and we know the resistance. Therefore, using Ohm's law, we can calculate the current in that resistor. And that works out to be about 1.37 amps. Again, I'll give you a shortcut for this in the next class called the current divider. All right. Well, that was a marathon. Let's go back and review the highlights of this lecture. Keep going and going and going. That Dahlen guy never shuts up, does he? Oh, okay, here we go. Series parallel circuits. Whoops, actually there's one before that. We talked about series circuits, and we said that in a series circuit, the total resistance is simply the sum of the individual resistances. Okay, that was easy. Next, we talked about parallel. And we said that this equation here describes the total resistance. And we used the calculator with a bunch of examples. And the more you use the calculator, the more or the easier that will be. From there, we moved to series parallel circuits with a recommendation to take each piece and redraw the circuit, simplifying as you go. And I understand nobody likes to do that. It's a lot of work, but it's very useful so you can see how the pieces fit together, especially when you're first starting out. That problem looks like a wonderful test problem where you're given the total resistance and you're asked to solve for the resistance of an individual resistor. All you're doing is using the parallel formula backwards. You could do the same thing with series, but that's almost trivial. In this, we're solving for power, but this was just a combination problem where first you had to calculate the total resistance and then you could calculate the power. This mess here, the trick was to find the current through R2. In order to do that, you had to divide the problem into segments. This box was very important to us because that allowed us to focus in on a very particular piece of the problem. We found the voltage across the nodes in that box, and once we knew the voltage, we were able to calculate the current through that resistor. This looks like a quiz or a test problem. Given a bag of 5 ohm resistors, how many different combinations could you come up with? This looks like another test or quiz question where you have a power supply and then 2 resistors, and you're asked to figure out how many different combinations could you come up with. And we determined that with 1 power supply, 2 resistors, there were 4 different ways to configure that circuit. You could configure it as series, single, or parallel. This last problem was really just a rework of the problem that was up here. So those are the same problems. I just worked it twice. Maybe you noticed that. Well, different values, but still working it twice. That's it for today. I wish you a safe weekend.